第二个. Yeah. So previous class must understand what's going on there, and you can also like this, as you can compare image your exact image to a pattern you can compare, and you change from image to a target histogram equalized format. So it's a very standard automatical enhancement technique. But today we are going to apply some different approach for enhancement. So previous we introduced a lot of different way for point operation, right? So we use some image negative, contrast extraction, compression, dynamic range, and subtraction, averaging, histogram operation. Now we are going to do some mask operation. So it's not pixel gradable transform to another pixel graded intense label, but now we do some mask operation. So some convolution idea, correlation idea, you have to understand clearly. We will give you some idea. Okay, so this is the mechanics of linear transformation. Actually, for your transformation for this mask, we have a linear and nonlinear approach. Okay, linear transformation and nonlinear. So for the linear, will be taught in these two lectures. For the nonlinear, will be next one. What's the nonlinear? For example, like a median filter, like a maximum mean filter, or some morphological operator. Morphology is also one of the chapters in our textbook. So if you are interested in for the nonlinear, for your research, you can go to the maybe chapter 9 or chapter 8. Okay, so what's the mask operation for image processing? This here we can see it's a magnetic linear spatial filter. We are talking about the linear first, okay, in these two classes. So let me write down this equation for you. We have this one, so we add a new page here. So let's write a linear spatial filter in mathematical form. Okay, so normally we have the output of GXY. What do we do with our input fxy? So we do this operator here, s from minus a to a, t from minus b to b, and this is your mask w, s, t, and times f of x plus s, y plus t. So look at this formula. So this f is your input image here, and w is your mask, design mask. So if you look at this formula, you can see the x is the dynamic parameters from minus a to a, from minus b to b. So which means your mask is with size 2a plus 1. It's the height 2b plus 1. So this is your mask. And it should be odd number. Okay, it's easier because your center here, you have right hand side, left hand side, upper side, lower side. It should be an odd number. Okay, for example, like 3, 5. 3 is the minimal size of your mask. So this mask multiply your image f xy here. So what do? We just turn around 1 by 1. If it is 3 by 3, if it is 5 by 5, so 1 by 1, just overlap, and then calculate according to this pixel. So 1 by 1 go through all the mask pixels, overlap with your original image, and then multiply individually, multiplication individually, and then sum up together. So this is the idea for this kind of operation. Okay, but we call this is correlation. Okay, so you overlap with the mask, doing nothing, just overlap one by one, and then pixel by pixel, move through the mesh, move to next step, move up to down, left to right, up to down, one by one, and you get a new image, and we call it a GSY here. So it's just a very easy operator. W, and this is the X through image here, and then step by step, sort of nonlinear. So here is a linear operation here, multiplication, sum up, it's all linear filters. What's about the nonlinear? Nonlinear is, for example, like this one, you mapping with some FSY here, and then when you overlap, you are not going to do some multiplication and summation. You just compare, maybe compare, and to find out with this size, and we find out the maximum value to replace it. We call it the maximum filter. You find that all the value, the smallest one, to replace this FSY, we call it a minimum operator. If you apply some morphological operator, we have to do some opening operation, closing operation, dilation operation, eroding operation. So therefore, basically from the fundamental operation for morphological operators. So it's combined a lot of nonlinear because you are not going to multiply and then perform some summation. So it's called nonlinear. But however, for this traditional one, we call it linear. Okay, linear mask operation here. And the other one is this is correlation. So when you do this one, it's easy because you just keep design a mask. The mask is the key. How you design a mask, you will get different results. And the other one is convolution. So correlation versus correlation, convolution. They are different approach, but they are all linear operators. So what's the convolution? So it's an important filter theory. And the convolution is you have to turn your mask from left to right, from up to down, before you do multiplication summation. So so here we maybe we use a new symbol for this one. G equal to W correlated FSY. So we use this is a small one. In your textbook, they use star, empty star. Okay, so traditional in mathematics, we use circle, ring, a ring, okay, empty ring. And the other one is convolution. Convolution is we use this star to perform this operator. So how do you do that? What's the difference between correlation and convolution? The only difference, your W, your mask, have to turn up, down, upside down, and left to right, rotate in 180 degrees before your multiplication and summation. That's the difference. But the result totally different, no? So if you define this one, what's the result? So it can be right the same as this one, summation S from minus A to A, T from minus B to B, because your mask size is the same. But in your here operation is either you rotate your mask or rotate your image is the same result. Okay, so if we rotate one of the image, we can write this is X minus S, Y minus T. So see, it's different. So in terms of this rotation before your multiplication and the summation, we call it convolution. So later on we'll see what's the difference before this these two applications here. Okay, so just image is 2D, right? But for easy to demonstrate the difference with one. Okay, so if our image is like this, origin, it's I'll magnify this one. Okay, so your image is like this. There's only center one, value one, and all the other pixels, negative pixels, zero. Next, with different coefficient, 1, 2, 4, 2, 8. Okay, so there are 5 pixels in W. So so centers here. Okay. So the first centers here. Okay. So you have to put this center from negative infinity negative position from far away from here, and then step by step go through until it hits the first pixel. Your center hits the first pixel, and then multiply corresponding value, and then sum up together. So what will happen if your image is a size of like this one, size of 1 by 7? This is a 1-dimensional signal. Signal 8 pixels. What the result will be if you correlate it with this signal? What the result will be? So imagine when your signal is 4 is here, they will touch this pixel, right? You're moving from negative infinity, go this way, and then step by step until here there are two boundaries. I didn't go there, but I already hit your signal. So actually, for the correlation and convolution, there are some border issues you have to discuss. Because your mesh size is larger than 1. So if your size is 3 by 3 or 1 by 3, I mean, you need some extended, some neighboring pixel before your operation. Or you are operating this correlation or convolution operation. There are 3 different ways to do your border consideration. The first one is don't care. Don't care. What do you mean? Don't care. So when your center mesh come here, fall in here, you can touch this one, but you don't know what's there. The outside your image, outside of your signal is nothing. So we don't care. So we cannot do anything. So go. Next one. Until you hit this one. The third pixel for this example, when your mesh is go here, it's on 4 here to overlap with this one, and now you can do some multiplication, summation. So which means I will skip these 2 pixels. So if you don't care, your result will shrink a little bit, depending on your mesh size. So don't care is one of the approach you can do. But the second one is more reasonable. You pay in 0 in your outside. So for example, this one W is 1 by 5. So you have to pay this 2 pixels outside, 2 pixels in your neighboring, in either way. Okay, so it's paid in 0. It's a very easy one. You just extended your image first. It's 0, pending outside. But after the result, you just give the center, the same size of your signal, our border discarded. So that's the way, heading by 0. The third way is called mirror replication. What's a mirror? It's just you wash your face in the morning. You look at a mirror. So outside, like this one, we padding this one. This is 0, 0. So just corresponding. If this is 1, we just padding here is 1. Here's 0. So it's a mirror condition. Okay, it's another way. Why you do this one? Because you just want to continue your border intensity, border signal. That's another way. So there are 3 traditional ways to process this kind of filtering. Okay, one is don't care. But if you don't care, your image output will be shrinked. Okay, only the center part. Okay, take away the border will be true result. But if you think it's not easy, you can paint in outside 0. Or the third way, use mirror way to paint in. So it's like a copy your border to your outside, not use zero. Because if you use zero, when your when your when your when your border it has some higher intensity level, but if you painting with zero, it will become an edge, a curve. So the result will be a little bit exaggerate. So we'll see some example in the textbook later. Okay, so let's come back to here. What do you do? We are going to do some correlation, and now is center is here. Your mask. So you don't do anything. You just shifting from negative infinity from right hand side. If you image left to right, up to down, go every pixel. So here origin here. So we see if we put here we paid in zero. Okay, sorry, they already paid in zero here. So here you will match here and like this one, starting position alignment. So we can see at this here at this pixel position, they multiply together and see 1 multiply 0, 2 multiply 0, plus 4 multiply 0, 2 0, and 0. So everything is the result is a 0 because 0 multiply everything will be 0. So the output will be like this one, right? So that's the result. If you do nothing, you just multiply corresponding position, intensity value, and then sum up together. So one by one. So next one, move here. Okay, here. Okay, starting position here. The next one will move to here. So you just again multiply the corresponding position, sum up together. So the output will like this. So one by one, shifting, right? The first one is 0, 0, 0, sum up 0. The second one will 8, sum up 0, 0, 0, 0, multiply, result. And so the second position will be 8. The first result will be 0. The third one will be 4. So you can see the result. What's that? No. The next one should be 2 here. 1, 2, 4, 2, 8. So the next one 2 and the next one 4. So you can see 0, 8, 2, 4. 0, 8, 2, 4, blah, blah, blah. This is the correlation. It's just use your mask, do nothing, and then move from minus infinity to positive infinity. How about convolution here? So convolution, we said before your multiplication and summation, you have to rotate, flip your mask, either mask or image. One of them have to flip. The result will be the same. Okay, you have to flip one of your mask and then multiply corresponding position, sum up together with our output. So in this example, our W, so rotated W, because it's one dimensional. So you can see it's right left to right. So 1, 2, 4, 2, 8 become 8, 2, 4, 2, 1, right? Just rotate. Corresponding 0 center point here. So we call it convolution. So now we are going to shifting for this mask from negative infinity to positive infinity. So go through step by step. So the same, go step by step. The first one will be here. Also, this is padding by 0 already. So multiply together, multiply, and then sum up. So the result you can see, and then this mask from here to right, left to right. So you can see multiply together. So result will become like this, convolution result. It's different from our correlation result. Right? Must be, because your mask is not a uniform. So come back, think about the mask design. The mask of this one. So the result totally different. It can be expected because your mask is not uniformly distributed, not symmetrically distributed. So if now I'm design my mask is like this one. 1, 1, 1, 1, 1. Right? 1, 1, 1, 1. Could you please tell me when you rotate your mask, what's the difference? The same, right? The same. So the result will be the same. If your mask design is a symmetric mask, the convolution and correlation result look like the same, right? Should be, right? So actually it is. Okay, so because you turn up left to right, turn up to side down, the result is the same, those relative is the same. But unfortunately, some of the mesh should be different, and they theoretically are totally different. Later we'll see some property, mathematical property. But now we just show you the difference because our mask design is not symmetric with respect to the center point, not symmetric. That is 1, 2, this is a 2x, so it's not symmetric. If it is symmetric, the result should be the same. You multiply together, sum up together. Okay, so this is the final result for these two different masks. And the extended for correlation, extended convolution. So I will just mention why it is extended. Because before you perform the correlation operation and convolution operation, you do some padding zero test first, padding outside. But we say if you use padding zero, the result will give you some very ugly border result. So let's see here. How come? This one. 为什么变成这样子 ？Anything wrong？ 哦，反白吗？还是？ The background, something wrong. It sounds weird. The background will be become. Okay, that's fine. Okay, so it's from a textbook slide, so you can look at. They just emphasize the figure, the caption inside. So now let's see a two-dimension image. So that's what we mentioned, how you padding your outside. So if your image is 5 by 5, now you are going to operate with some mesh is 3 by 3. How do you do? 3 by 3. So how many pixels you are going to padding your outside of your image? Should be 1, right? So 5 by 5 should become 7 by 7. You know why? Because your mesh outside there's one more pixel in left hand side, one more pixel in right hand side. So when you put on your mesh here, so there should be extending one more mesh here. So this is the outside original image here. So outside should be padding left hand side, or one more column, and one more row in your image. So initial position will be like this one. So it's after convolution, you take inside. That's the real result. So for this correlation result, can you expect? Here is one image. Actually, this is impulse function. Impulse, only single value in this image. All background value is 0. So it's an impulse. Actually, if you perform correlation on this mesh, 1, 2, 3, 4, 6, 4, 5, 6, 7, 8, 9. What's the result? Wow, it looks like a little bit weird. It's just upside down of the mesh value, right? 9, 8, 7, 6, 8, 4. So this is a correlation result because you don't still rotate your mesh in the range and then do some linear calculation. So result like this one. But how about for the convolution? Convolution here. Oh, okay. How come? Sometimes disappear, sometimes okay, anyway, let's see correlation. Exactly the same mesh, but I perform the correlation with this impulse function. But correlation, when you try to operate correlation, you have to rotate your mesh left to right, up to down, and then go through the mesh operation step by step. The result will be like this. That is the same spatial order of your data. And which one is the good one? Actually, for our system theory design, the theory will be convolution. Okay, it is not correlation operation. So if you design the real filter in your hardware system, the relationship between your system mask and your input image, they perform convolution relationship, convolution algorithm. So for the example, that is some impulse function. If I want to know what's the filter inside your system, I just input impulse image. We call this as an impulse function. So for a two-dimensional, it's an impulse function. So it's just like this one. It's an impulse at the center, nothing outside. So impulse, mathematically, we use this one. Come up with any signal, the result will be itself convolution like this. Okay, so you can see convolution is a much more important operation in your system filter design. And result, so it is. Okay, every impulse convolve with the new image, the result will be itself, but correlation is different. Correlation is different. So please make sure what you are going to write on your code is a convolution or correlation is different. Okay, so now let's see. Some fundamental property of convolution and correlation in the system. So we just use very easy property like a commutative. What's a commutative? You know, in some 5 times 4 equal to 4 times 5, right? It's called commutative, right? But for the convolution, no problem. Okay, we say we use convolution and the correlation. Convolution, unfortunately, correlation didn't satisfy the commutative law. Can you imagine that? Why? And associative is mathematics like this. We apply the this G to H convolution first, and then convolve with F later. Exactly the same. F convolve G first, and then convolve H later. It works for convolution, but for correlation, it doesn't work. So now they are totally different. Okay, but for this distributive, it's okay because it's convolve with this one and edit with another one GH, and then equally the same. The correlation, okay, it works for this distribution property. But the other two different. Why? How can you prove it? You have to go with mathematically one by one. I will give you some example. You can try. Okay, try to calculate and see if this is really doesn't work for this commutative and associative. If you use the symmetric mask or positive mask, you didn't see the difference. I'm sorry, it's a wrong example to show the correlation don't hold this commutative property. But here, if you use like this, okay, let me think. Easy. Let's see if I have a vector is 0, no, 1, 0, minus 1. Okay, as your mask. And then correlated with 1, 2, 3, 4, 5. Oh, very easy. Can you do that for me? Quickly. Very easy, right? Just center to this one. This is your center. And then step by step. Okay, if you like the star, it's okay. Okay. Okay, in class they use empty star as correlation. What's the result? What's the result? You have a result here. Okay, so if you heading 0 here, heading 0. Okay, so let's do 0, 1, minus 1. Correlation should be multiplied, right? The mask don't rotate directly. So what's the result? The result should be minus 2, right? The first pixel, right? No one agree with me. I don't know how to go. Is that right? Yeah, okay. So how about next? 1, 0, -1. Or this one? What's the result? Correlation. How much? Huh? -2, right? This times 3. -3. Plus 0 times 2, 0. So -3. Plus 1 plus 1, 1. So -3 plus 1 is a -2. Right? Thank you. How about next? How about this one? 1, 0, -1. What's the result? -2, right? Okay, thank you. Keep going. -2. How about this one? -1. 4, right? Okay, you can go further. Okay. 1, 0, -1 is 4. And this one is 1, 0, -1 is 5. And then here is if you're going to every number here to be 0, okay? Complete result like this one, right? So this is W correlated with A. Now please do what? We are going to demonstrate commutative. So we are going to do this one. Right? I want to try to prove these are different. So please calculate for me. If you rotate these two signals, is that result the same? So let's do. Okay, so it's you have to padding 0, blah blah blah. So when you have a 1, 2, 3, 4, 5. So when you hear is 5, and 1, 2, 3, 4, 5. So the second is 3 minus 3 minus plus -5, so it's a -2, and the next one. Oh, sorry, this is -2 here. Position is wrong. So this is a 5 here, and this one when you 1, 2, 3, 4. This one here is a -2. Right? Result different. Now you're going to ask me, how about convolution? Convolution satisfies commutative. Do you agree? So let's see. And this is 1, 2, 3, 4, 5. Please perform convolution for me. How do you do? For convolution, you have to rotate one signal first, and then do the shifting operation. So the should be rotate, so become -1, 0, 1. So shifting one by one. Okay, so let's see. If you heading 0, so from here is a -1, -1, so it's here's 1, and the next one is -1, 0, 1. So it's a 2, and blah 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 blah, -1, 0, 1. It should be 2, and -1, 0, 1. It should be 2. Now we are going to demonstrate some commutative. So how do you do? You have to do this one. So please do this convert with 1, 0, -1. Okay, so how do you do? Or you also rotate this one. So it's rotate first, and then multiply summation. step by step. And interestingly, the result is exactly the same. Okay, I just use an example to demonstrate. So you have to go back to calculate by yourself, one by one, to do that, put it in your mind. The correlation doesn't satisfy community. The correlation doesn't satisfy this the other associative property. Only distributive. These three operators work for our linear system, but correlation doesn't fit these two. So we cannot change, turn around this mask and image. So it's different results. However, convolution works. Everything. I think wow. Okay, so since we come to convolution, I still have to give you some idea. If you don't know the convolution, okay. So I don't know, is anyone already get the result here? Exactly. I promise it should be the same. Go home, do it yourself. So now let's see what's the convolution. Since we have this one, we use a 1D convolution. I am afraid some of you didn't know the signal processing in advance. So let's do one example here. Okay, so 1D convolution. If we want to use this one function combined with this one. Okay, what's the definition? Actually, it's just as we mentioned. Okay, it's rotate one signal and then sum up together, step by step. So in mathematically, we do this one is defined like this. Use new parameter G, rotate this one and then multiply. So like the summation we did in previous example. Now we are going to use one simple example to let you know what's the mathematical background, because we have 10 minutes left. So let's see. Can you imagine if this one combined with this one, what's the result? A square combined with a square. It should be triangle. It should be a triangle as a result. So what do? We just rotate one signal, and then from minus infinity, step by step, go through, and then see an overlap area, step by step, and then summarize, and you will get the result. So now let's use this example, to see the result. Okay. For example, if we have one signal, it's like this. The length is 1, 1, and combined with a signal, it's smaller one. It's like this, 1/2. So this is our f of x here. This is our g of x here. So we have two signals, square. Okay, one. The other one is the amplitude of 1/2. So how you do this one? So actually, we rotate one signal from minus infinity, step by step, go through, scan through the target signal, and then sum up together. Actually, the sum is the integration, sum up together. So we'll do this one like this. First, we keep this signal not moving. Move this 1/2 signal. So we'll go like this one. Rotate. So your front end, if we put this is the parameter x, because a new parameter like t tau here. Okay, like tau here. So it's a new signal parameter tau. So we put in the tau system, and we rotate this one. So you rotate, and your front end is the x parameter. So the next one is because the width is 1, so this should be x minus 1. Okay, this location, because the width is also keep as 1 as its width. So this black rectangle moving from minus infinity and then approach to right until hit the original signal here. We call it convolution. So combine you rotate and then move from left to right. So see, until your signal hit, go here. This is x. This is x minus 1. So when your here is 1. When your x is between 0 to 1, they will have some overlap with some original signal here. Right? It's moving. If the x is still less than 0, it will be no, will be 0. So when x smaller than 0, the result is. But now x is between 1 and 0, moving. When your x located in 0 and 1, now we have some overlapping. What's the overlapping area? It's so we are going to do some equation. So we have this range from 0 to x, and your original signal times original x minus tau and d tau. So what's the result? So you can see when your x moving right until hit the f signal, they have some overlap area, the slanted area here, and the result will be 0x, f keep constant 1, and the g keep constant 1/2. Can you do that integration for me? The result will be tau 0 to x. So it's 1/2 tau minus x. Yeah. So see, when your x located is 0 to 1, their overlapping area is this function 1 divided by 2 multiply your x location. So you can see the area getting more and more until all the square overlap together, and the image, the integration result will be 1/2 the highest value. So how about your x is moving outside this rectangle? So let's see, keep moving, and this here is 1. So when your is here, so which means x is here and x here. Here's a x minus 1. So if you look at this area, they should be like this. So when your x is larger than 1 but smaller than 2, actually 2. If your x larger than 2, there's no overlapping anymore. So x is located with 1 and 2, and your overlapping area will be the left-hand part. So what's the area? So you are going to calculate this one. So the result will be x minus 1 to 1, because the region, overlap region, only from x minus 1 to 1. And the output, it depends on this signal, the same. So equal to what? This is 1/2 d tau. So the same, it's 1/2 tau, and from x minus 1 to 1. So the result will be 1/2 minus 1/2 x minus 1. So it's become what? Become 1/2 plus, become 1 minus 1/2 x. Okay. So see, everything, we have the result here, corresponding result. How about next? The next one will be x larger than 2. So what's the result? If x larger than 2, here's 1, x larger than 2. So which means x larger than 2, 2 is here. So x minus 1. So there will be no overlapping with this original signal at all. So the result will be 0. So you can withdraw and draw this result. So when x smaller than 0, when x smaller than 0, the result is 0. When x between 0 and 1. And it is become 1/2 x, so it's not like this one. The height will be 1/2. And when x between 1 and 2, so the result will be 1 minus half of x. So what's the result? When x is 1, it's 1/2. When x is 2, 1 minus 1 is 0. So the offset will become like this. So our result will be, output will be like this one, like a triangle. So two square combined together, the result must be triangle. So that's the result. And you can see this one, combine this one, the result like this one. So that's the convolution for the 1D signal. Now we have a 2D signal. I already told you how to do it. Rotate your mask right to left, up to down. And then pixel by pixel, do multiplication and summation. So that's what we do, multiplication and summation. Okay, so that's the convolution. And please remember, they have different characteristics. Convolution is a system kernel knowledge. Okay, but correlation is just you do nothing. You just use mathematical to do it. But in your system, real system, it perform convolution. Everything will be like this one because of the time, step by step, they will do this result. So this is the example that let you know the result of the convolution. So please know how you do it. And the next one, we are going to see how we design the mask. Okay, as long as you know the correlation operation, and what's the next to design your mask, how you design it, and what's the result you are going to see. Okay, so it's a different story here because of different size, you have different filter function. For example, like this uniform mask. Very easy, uniform. You just use 1 in every pixel, and then remember to divide the summation of the pixel value. And this is the Gaussian. So why you do that one? Because next time we will also tell you the function Fourier transform domain and what's the performance. Okay, so for the square, you design in your spatial domain uniform mask, and the Fourier transform will like this one, like the sinc function. So it's kind of low-pass filter. How about Gaussian? The result will be Gaussian as well. So it's low-pass filter for sure. Okay, so next time we will see how we design some mesh. Partial size is good for the uniform and for Gaussian. Because if you didn't use the right size, your Gaussian didn't give you the best result. The answer is the 6 times of your sigma, your Gaussian width. Okay, so today please take home message is convolution. If you don't know the theory here, you will miss one of your midterm quiz. Okay, so our class stop here. Have a nice holiday next weekend, right? 4 days holiday. Okay, enjoy it. When is the homework due? October something, right? We are going to give the second homework soon. Okay, so please finish your first homework. Yes.
Question at the midterm exam.
Yeah.
Is it just can you use MATLAB or calculator or just binary?
Very simple calculation.
Okay.
No worry. You don't need a calculator. You don't need a computer.
Okay.